So this talk is based on our paper, which is titled Google's Multilingual Neural Machine Translation System. And then we have a colon, and we say, enabling zero-shot translation. So my name is Melvin. I'm from the Google Translate team. But this is joint work done with many people from the Google Brain team and the Google Translate team. First of all, happy International Women's Day to everyone. So why do we care about translations? So about 50% of the internet is in English, and only 20% of the world's population speak English. And on the right, you see this graph. These are the top 10 languages on the web. English, Chinese, Russian, German, Spanish, Japanese, French, Polish, Korean, and Portuguese. And they make up about 80% of the web. And you notice that languages like Arabic or Hindi, which makes up about 300 million speakers each, they're not even in the top 10. So Google's mission is to make this information accessible to everyone. So we definitely need translations. About Google Translate is we have about 1 billion translations every day. And we have about 500 million monthly active users. And we support about 103 different languages.
Question on your last.
Yeah.
So I've actually spoken with Portuguese, and the thing they point out to me is the vast majority of Portuguese are in the Brazilian domain, like
Right.
5 times as many.
Yeah.
So you're saying that, are you using the PT there or any of the others?
No, we club both of them. It's
Okay.
not, we don't distinguish.
That's fine.
Yeah.
That was not clear.
Yeah, and please ask questions. I have a lot of time. Yeah. I have a lot of time. Yeah.
Language codes, not country codes.
So about this slide, one interesting thing about Google Translate is one of those products where 95% of usage is outside of the US. So our top countries are like Brazil, India, Mexico, Germany, Italy. But you'd expect every other Google product has 90% usage in the US and 10% elsewhere.
How do I know it's you?
Well, machine translation. So it started with Warren Weaver in 1949. He used this tall towers analogy. So you're in a tower on the left and you want to communicate with someone on the right. He says, do not shout from tower to tower, but go down to the common basement and try to talk to each other. And he was hinting at some kind of an interlingua which exists in the basement. And let's look at a brief history of machine translation. So it started with in the 1950s, and then 1960s, Sistran, which is the first machine translation company, was founded. In the 1990s, people were doing IBM models, word-based models, and then people started doing statistical MT. And in the 2000s, there's this thing called phrase-based machine translation that became very popular, and that started being the state of the art for over a decade, actually. And then you started seeing applications that started to use deep learning, which is using these neural networks. And the first success was in speech recognition, but slowly it caught up to machine translation. So about 2014 was the first neural machine translation paper. And then 2016, there was our paper from Google. But a lot has happened between 2014 and now. So here is, well, before that, here is a quick intro about what phrase-based machine translation did. It split the sentence into a bunch of pieces, and it translated phrase by phrase. And at the end, it tried to put it together like a puzzle piece. So it translated one puzzle piece, the next one, and then it tried to stitch it together. But when you have a neural machine translation, this is an exaggeration, but you can think of it as a painter trying to paint it from scratch. So it's trying to make continuous and a global decision instead of making these local decisions. Here's what's happened in Neural MT from 2014 to 17. So you initially had the first paper come out, then there was a paper on large vocabulary, NMT. Then we saw the same architecture being used for image captioning. OpenMT in 2015 was the first public competition that had a neural system in it. WMT15, also the first WMT that had a neural system in it. A bunch of work on subword neural machine translation. People started doing multilingual neural machine translation, multi-source. WMT16, by that point, the 90% of the winners were neural machine translation systems. So it had already started to change. And people were trying to do zero resource neural machine translation. Then we had Google's paper and the papers on fully character neural machine translation. And finally, the zero shot translation. But you can see that there's a lot happening. A lot of people are looking into it. And it's an interesting research topic. So just a step back, what is sequence modeling? So you want to predict the likelihood of a sequence. So what is the probability of this sequence, right? And a sequence can be a picture, a video, some speech, or it can also be a piece of text. The typical example is a language model. So in a language model, you want to say how likely is a given sentence. So you will model this as a product of these conditional probabilities. And in an n-gram language model, you would have the nth order Markov assumption, which is that you only depend on the previous n minus 1 words, and you don't depend on anything else. But we want non-Markovian sequence modeling, which is, in Markovian modeling, we ignore anything that's beyond the context. But in non-Markovian, we want to support multiple variable length sequences. So you would end up having to model the entire sequence, right? And they have to be variable length. So what's one way to handle variable length sequences? You use recurrence. And that's where these recurrent neural networks come into play, called RNNs. So here's a small example. If you wanted to model this sentence, the cat sat on with an RNN. You'd have the input sequence, and then you have an internal memory state, which is the one in purple, that keeps track of the state at each time step. And then you need a function that takes, at each time step, the input and the memory state, and it can recurse at each time step. So you'd have probability of the, and then you'd have probability of cat, given everything else, probability of sat, given everything else, and so on. Some more information about RNNs. They technically have unlimited depth because you can unroll the RNN.
Can you go back one slide?
Yeah.
So, in order to do that, you have to have a vocabulary.
Yeah.
And you have to have a complete representation of the vocabulary.
Yes, you do.
But that may work for French because of the Académie Française, but it doesn't really work for English because English is constantly creating new words.
That's a good point. So I actually get to that in a bit. But that's an interesting question, right? If you have a machine translation system or you want to model a sequence, you need to have an open vocabulary. So you need to support everything, right? And I get to that in a little bit. More information is they have unlimited depth. They're general computers. So they're also universal function approximators. So they can learn any program. So you can think of it like this. There's an input at every time step, and then there's a recurrence, and it outputs a memory state that you can use. How do you train this RNN? Is you unroll the loop, and you apply backpropagation as you do to every other neural network. So you would backpropagate through time. And these RNNs have problems in that they have this problem of vanishing or exploding gradients. Since the sequence is too long, as you go further down the sequence, your gradients can explode or vanish. And as the name suggests, you need a long-term memory, which is why we use long short-term memories. They were founded back in 1995, but they're very popular now. So this is what we use. So this is a vanilla RNN, and then there is an LSTM RNN. But for most practical purposes, you can think of an LSTM as a black box, which is just a better RNN that you can use. And from sequence modeling, now you want to get to sequence modeling. So you have an input sequence, and then you want to map it to an output sequence. And here we call the left side what is called an encoder. The encoder is trying to encode the input sequence. And then on the right side, you have the decoder, which looks at the encoding of the input sentence and tries to predict the output sequence. And since we already said, because we're using an RNN, we can support any sequence lengths in both the input and the output. So here's the encoder, which is in pink. So the cat sat, and you can see that at each time step, you're trying to model the sequence. And at this point, this representation, you're actually modeling the entire sequence in that representation, in that one vector. It's a vector of about 1,000 numbers, and you're modeling the entire input sequence in that one vector. And now you want to decode. So based on this, you want to predict, oh, what is my first target token? You're going to say D, and then again, you predict what's the second, given that I predicted D, Katsa, and then the next word. And you keep doing this until you encounter an end of sequence token. So when the model produces an end of sequence token, we say, oh, okay, we're done decoding. Here is the output of the model. So you can stack these sequence to sequence models. So you can have, instead of having just one of these layers, you can have multiple layers stacked on top of each other. And yeah. And then there was a bottleneck that I talked about, because here you see the encoder is trying to encode the entire sequence. And then when you want to decode, we use this mechanism called the attention that is trying to pay attention to every input in the encoder. So when I'm trying to predict the first token, I can cheat and I can look up every one of the encodings that I want to look at. And the darker the line, the more the attention it's giving to that sequence. So when you're trying to predict the first word, say knowledge, you would want to pay attention to the Chinese word that means knowledge much more than the other words. So you can see that there's a dark line, and then
Question?
Yeah.
But you don't look backwards?
you don't look backwards.
When you're in the second one, you don't look at you don't look back one in the sequence.
You do look back at the last token you predicted.
Okay.
Yeah. Yeah, you do. Like you know what you predicted previously. So when you're decoding his, you know what.
In the last one, you don't look all the way back.
You don't look all the way back. You just look one back.
Actually, if you look at the pictures, there are lines which go to each source word, but some of them are almost transparent because the weight of this is 0. The way it is implemented, it computes a weighted sum over the source sentence.
The grade to the point of flight.
Yeah.
Oh, I see. So the words that are closer to it probably influence that word, so they have a higher weight.
Yes.
And the ones that are further away have less influence
No,
on
it
the current
depends on
context.
the ordering. So
Right.
it's similar to how a human would do it. So when you have a long sentence, you read the entire sentence, and then you start translating, and then like, oh, I forgot what I had to translate. I go and I look back. It's like, okay, I have to translate this segment. I translate it, and then you say, oh, I have to translate this segment. I go, I look back. You kind of give a mechanism for the model to attend to different things.
This is a mechanism. It's called soft attention because it computes a probability distribution of a source sentence and then takes a weighted sum. So when it looks at this word, it's actually looking a little bit all around, but mostly at this word. And there is also hard attention where the network is built differently and needs to be trained differently. Right? It strictly ignores everything else and just looks at one.
Well, we use
This is not what we're doing.
Yeah, we use soft attention in our models. So this kind of solves the bottleneck problem. Like you had all of the input sequence in one vector, but now you can kind of cheat and go back and look at the entire input sequence. So when you put all of it together, this is our architecture for Google's system. So you have a deep encoder and a deep decoder, and you can see that there's an attention mechanism in the middle that the model uses to pay attention to things. Things are parallelized using GPUs. So each of these layers run on a different GPU, so they don't have to wait for each other. And at the top, you have a softmax, which predicts the token at each time. But it's there's a lot in the picture.
And the Y's correspond to every single word that's possible.
Yeah,
Okay.
yeah,
It's a huge softmax.
exactly. So getting to the next slide. So you have a vocabulary size problem. So you have to support all of the words that you want to decode. And for example, dog or dogs in Russian, if you wanted to cover all of its forms, you would need 130,000 words. So this form of dog is the 138,000 word in the vocabulary. So you would have to support all of those. And if you go even further, if you want to support dog breeding, then you need about 2 million vocabulary elements in your softmax, right?
Give some examples. How do you get to 100? How do you get to these large numbers?
It's just the frequency of all Russian words in a corpus.
So on this picture, the words are shown in frequency order in the training corpus. So we assume that if we want to use a vocabulary of 100,000 words, we will use the most frequent 100,000. So now all the word forms of dog in Russian, they occur in this vocabulary and they occur at positions 12,000, 13,000 and so on.
Thank you, that's a big help.
So if we take the top, we will need, on the right we will need 2 million, and this will only cover a few variations, and all possible variations may be not even present in the corpus.
Yeah, so because of that, we use subword segmentation, where we segment each word into different pieces based on frequency. So now you can see that this word for dog is split into 2 tokens now. So now you can model them with just 32,000 words. And then the word for dog breeding is actually split up into 3 tokens. And this token splitting is done based on frequencies. So you would you would combine 2 characters. If they're most frequent in the vocabulary, you would combine the 3rd character as well if it's also frequent. So it's statistics-based splitting. And this splitting allows us to cover most of the vocabulary with just 32,000 words. But it increases the sequence length. So now you have longer sequences because you're splitting up each word by about 20 to 50%, right? So it's essentially open vocabulary by using these word pieces. So if you had a sentence, we realized that word pieces are the best choice. You see that most of the words are pretty common and they're not split, but something like realized, which is a little uncommon, is split into 2. And if you had another language, you're translating it to Tamil, you would have some words that are split, some words are not split based on frequencies again. And then now you have this problem of latency. So translation speed was a major launch blocker for us when we were building these neural networks, because you have these large networks which have to process these long sequences because we were using these subword units. And these neural networks are notoriously famous for large matrix multiplication, so they take a long time. Many other restrictions, like a lot of memory is required. So which is why we had these tensor processing units. I believe that's the talk that's going to be next week. We're going to talk about the TPUs. But Google invested in making these custom ASICs long back. So they realized that, oh, okay, we're going to use a bunch of neural networks. So let's build custom hardware to accelerate these neural networks. And we started building models that supported these TPUs. And we went from initially having 10 seconds to decode an entire sentence to about 200 milliseconds by using these TPUs, right? So you can see the latency. In the blue, you see the neural system, and in the red, you see the previous phrase-based system. And one thing to notice is the blue lines are almost flat, like they're constant. There's not a lot of variance. But the red lines, they vary a lot. Some of the languages have high latency, some other languages have low latency, because we were doing model-to-model tuning, like, oh, this language is bad, we would go and tune that model for that language and make the beam larger and things like that. But with these neural systems, it's almost flat. But they're still worse than the previous system. They're still like 2 to 3 times worse than the phrase-based system. But we did experiments where we showed users slow translations. We would take 1% of our users, show them 2 times slower translations, 3 times slower translations. And we didn't see a significant effect of doing that. So because we have much better quality with these models, we decided to launch them, despite the fact they were slower.
Sorry, what's the BNMT?
So that's our neural machine translation system. B stands for brain.
Oh, I see.
Yeah, that's yeah. And then we needed a lot of capacity, right? You don't need just one TPU, you need lots of TPUs to serve all of the traffic. And Google machine translation was one of the first users of TPU. So we essentially had a check that said use all TPUs at Google. And at one point, we were the highest users of TPU inside Google, just the machine translations. So we were replacing this system on the left, which is the old phrase-based system. It had lots of individual pieces, and each of them were optimized in a different way with a neural network, with essentially a large neural network. It does end-to-end learning. It's simple, but the results are much, much better.
In translation, we did a project recently with Multilingual translation, and we got into trouble because you have to speak in either the age or the depends on age, you're masculine or feminine. You have different translations.
That's a
How
good point.
about you with that in the end-to-end solution that you have?
We did some experiments on that, but let me get to it in a bit. But we do address that, not right now, but we can easily address that. So there are like different formalities based on if you're speaking to an older person, if you're speaking to a younger person, the translation changes. And the only way of knowing these things is to let the user say that, hey, I'm talking to this old person, he's male, give me a translation from English to Russian or English to Hindi. But right now we don't do that. We just translate from English to Hindi. And we assume the age, I guess. So when we started on this project, everyone said, oh, it'll take 3 years to launch. It actually took about more than a year. So a few people from the Google Brain team, they started in September of 2015 working on this project. And around February of 2016, they obtained the first large-scale results inside Google. And from Feb to September, a lot of people were involved, and we said, we put in a lot of work. We launched the first language pair, which was Chinese to English. And in November, we launched about 16 different language pairs. So how did it go? Did people like it? So we did a silent launch in Japan. So in Japan, we started serving them neural translations, but we did not tell them that it was neural. And people actually found out. So Google Translate in Japanese became the most trending topic on Twitter in just one day. So people were so excited because Japanese, for instance, one of the team members said it went from being unusable to usable, actually. The translation quality jump was huge.
And then how long did that persist? 6 hours later, was it back to zero?
No, we didn't check, but then the next day
That was probably wise.
yeah, but then the next day,
I checked and it was to zero.
okay. But the next day we announced it. I think in a few days we were announcing it publicly. So there's a good example. So there's Hemingway's "The Snows of Kilimanjaro." I think this was one of the first tweets or something. So there's a Japanese professor who took this piece from Hemingway and he manually translated it into Japanese. And he said, okay, this is my translation of Hemingway. I want to see how good Google Translate is when I get it back. So he took his Japanese text, and let me show you first what he got when you put it into the old system.
That raises a question on that particular one as an example, which is also, you can go to your next slide. And that's, so it points out there's 19,000 feet. Japanese now use metric.
Right.
So did he give them the meter?
No idea, but yeah, I'm guessing he did a faithful translation, what he thought was best.
You think that's the showstopper?
Oh no, wait. Yeah, wait till you see the translation. So let's just focus on the last sentence. So it says, no one has explained what the leopard was seeking at that altitude. So let's just focus on this last sentence. And if you put it into our old system, you get back whether the leopard had what that demand at that altitude. There is no that nobody explained. So it is, I don't know if you get anything out of it. But when you put it into the new system, it says no one can explain what leopard was seeking at that altitude. So it was almost perfect. And if you look at the whole passage, there's just 2 errors, and it was missing a bunch of articles. And so this guy was so excited by this, and he started tweeting about it, and that's how it started. But you can see the difference in quality from going from the old system to the new system. So some examples, the way we measured quality was we did a human experiment. We showed two systems side by side to humans. We would show a sentence in English, and we would show the old Japanese translation and the new Japanese translation, and we would ask them to rate it on a 0 to 6 scale. So 0 means very bad translation, 6 means very good translation. And previously, we would consider any significant gain would be greater than 0.1. So if your new system was greater than 0.1 compared to the old system, we would consider it significant and launchable. And when we built the first model, the Chinese to English model, we got 0.6, which was a large gain. And someone actually looked it up. So in the past 10 years, all of the improvements that we've made on Chinese to English was actually less than 0.6. So in just a single shift from phrase-based to neural networks, we got more gains than in the past 10 years put together. And for most other language pairs, we've been seeing greater than 0.5, some even greater than 1. Japanese, for instance, was greater than 1. So it would go from a rating of 3 to a rating of 4.5 or something like that. So here is more numbers. So we have on the human scale, 0 to 6, 0 being bad, 6 being good. You have the blue as the phrase-based system, and then you have the orange, which are humans. Human quality, it's just an approximation of human quality. It's just the average human. It's not the best translator ever, right? And then you have the neural system, which is in green. And you can see that in most cases, it actually bridges the gap by at least half. So sometimes it's pretty close. Sometimes it's halfway between the old system and the human.
What is perfect translation?
That's whatever someone's looking at it, he says it's a 6. That's a perfect translation.
That's a subjective opinion of a person who is rating.
Yeah, but we get subjective opinions from multiple people, not just, yeah.
When you show them and you have them rank from 0 to 6, they're bilingual people so you see the original.
Yeah, you see the original and you see both, and they're bilingual people. But one of the things we've noticed is this kind of presentation actually biases people in that if you had one system that was really good and the other is really bad, it forces them to push the scoring this way. Instead of giving it a 3 and a 5, they would give it a 0 and a 6, right? We noticed it, and we're starting to do single presentations. We would just show one system and then show the next system and aggregate later. But now then we launched a few language pairs. We launched Chinese, and then we realized, oh, this does not scale. So each of these models take about 2 to 3 weeks to train, and they need about hundreds of millions of examples to work really well. And with 103 languages that Google Translate supports, you would have to go and build approximately 103 squared of these models. And obviously, it's going to be impossible, even at Google scale, right? So we wanted to use multilingual models. So previously, we would have different models for different language pairs. You had an English to French model, you had an English to Spanish. Well, we wanted to combine all of them into a single multilingual model. So we wanted to build a single model that can translate all of these languages together, right? And the way we did it was the simplest thing we could think of. We would prepend the source sentence with a token to indicate what the target language is going to be. Let me give you an example. So if you had a source sentence and you want to translate it into the target sentence, for example, if you had this English sentence, and that's the translation, we get as ihnen, you would add this token at the beginning that's saying, oh, this sentence needs to be translated to German. And then if you want to translate the same sentence to Spanish, you would add another token that says, oh, this is going to Spanish. And if you want to translate to English, you add this English token. And now you would just take the data for different language pairs, you would add this token and combine them and just give it to the neural network. So this was the simplest thing we could think of. And it actually worked, right? So that's the brilliant part. All of our models right now that are multilingual use just this thing.
Why didn't you need a source language token as well as
That's a good question. So we wanted the model to be source agnostic. So one reason that I can think of right now is when you go to Google Translate, you don't have to select the source language. You can start typing, and the system will automatically detect your language. Now, when we put the source token, it kind of restricts the model and it gives the model more information. But we wanted the model to be as general as possible. So when you don't put in the source token, the model is actually source agnostic. It doesn't care about what the source sentence is. It only cares that it has to translate it into this language.
So now the output is a vocabulary from a lot of different languages.
Yes.
So is your softmax now even huger?
That's a good question. Again, in the next slide. So we still use 32,000 word pieces. And what we do is we equally represent them across different languages. So if you had a system that had English, Spanish, and French, we would take all the top words. And if an English word occurred 10,000 times, but a French word occurred only 5,000 times, but it's the first French word, we would make them equal. And our vocabulary would be multilingual. So it would be the most frequent English words, the most frequent French words, the most frequent Spanish words, and the word pieces would also be split based on the counts.
And you can do that with just 32,000
Yeah, we do. Yeah, we
all
do
languages?
that. All language. All. Just we use only 32,000. Yeah.
No,
Wow.
not for all languages, but multiple different languages with different scripts.
Yeah.
All 103 languages.
No. We don't use one model for all of them. We're not yet there. We just use 4 to 5 or 10 in one model.
How do you represent them? Because there's many character sets.
Yeah. We use whatever the script the language uses. So if it was a Japanese word, we would use the Japanese script. And if it was English, we would use the Latin script.
So in Japanese, there are 3 scripts that are used for every.
Yeah, we use kanji and hiragana. We don't change anything. We don't transliterate.
Yeah. You just take the most frequent Unicode characters. And for some languages, you need a few hundreds. For some languages, you need a few thousand.
And then same way, our training data is also represented equally. So if you wanted to club 4 of these language pairs into one model, we would look through the counts. If the first one had 10 million and the second one had 5 million, we would oversample the second one to be 10 million. So such that everything is equally represented in the model. So training takes about 10 million steps, takes about 3 weeks on roughly 100 GPUs. So it's a long time. You need a lot of patience. You press a button, wait 3 weeks, and then see what happens.
How did you get your training data? Did you?
So we get it from the web. We go to the web and try to mine parallel sentences. So if you go to bbc.com, we would detect that it's in English. And then if you go to the BBC website for Spanish, we would detect, oh, these pages are the same. These are parallel sentences. So for evaluating these models, we used what is called the BLUE score, which is a standard criteria for machine translation evaluation. And the higher the score, the better. That's all you need to know.
So with the training, do you ever get a problem where you detect that those 2 websites are the same and it turns out that they had just done the dumb thing and used Google Translate, and so you're just sampling what the previous bad translation?
Yeah, we have a lot of that problem. We still haven't addressed it. For some languages, it's as high as 50% is using Google Translate. So we try to watermark our translations, but it's not as reliable. But it's an interesting problem.
How about the Monty Python phrasebook,
I don't know.
where the translations are purposely malicious?
Yeah, we get a lot of that too, where,
If you feed your output back to as an input, is your system stable at this point?
Yes. Yeah, to some extent, it's pretty robust. No, to a large extent, it's pretty robust.
In order to do some error analysis to know that to improve the model quality, the quality of performance, do you need to have a more flexible model or more data?
That's a good question. It's always the case that if you have better data, you get better quality. So even with these neural networks, because they're end-to-end, everything boils down to the data. So there's a lot of data engineering in preparing the right data, and also in what data you see in which order. That also, people show that it matters that you see some examples before other examples and things like that. So it's more on the data side. So there are three different types of multilingual translation that you can use. So you can use that people have been using. So there's a many-to-one translation where you have many languages on the source, and then you have one language on the target. And you have one-to-many, you have one language on the source, and you have many languages on the target side, and then you can have many languages to many languages, right? And people in literature use they make a copy of these encoder and the decoder for different languages. But in our system, since we just add this token, all we see is just one red box, one green box, one blue box. So we have a single encoder, a single attention mechanism, and a single decoder. So that's it. And there are some results now, right? So we started off with doing many-to-one experiments, which was the easiest case. So you had many languages going to English. And you can see that there's a single model, there's a multilingual model. So the multilingual model, I have to clarify in this case, is the same size and the same setting as the single model. So even despite the fact that it models two languages, it's just the same size. And one of the reasons is you can make the model bigger, but then now you cannot serve it because it's going to be slow to train and it's going to be large, right? So we always stuck to the same size for all of these experiments. So now you see that the multilingual model is also already starting to do better than the single model. In most cases, you can see gains. So WMT is this academic data set, which is like a standard public data set where people report numbers. And prod is our production data set, our production system. And here it's a good story, right? Everything is positive. This is what you want. Now we did the harder case, which is going from one language to many languages, right? So in the first row, if you see that we have this oversampling, the English to German set is about 7 times less than the English to French set. So when we do oversampling, we would basically repeat the English to German set 7 times more and make it equal. But in the second column, we said, okay, what if we don't do this oversampling? What happens? Now you see that the English to German set, because it is outweighed by the French, it goes really bad. So we realized that we always have to oversample and make sure that the data is equally distributed across all languages. And you start to see some losses in the WMT setting. But in the production setting, because you have a lot of languages, a lot of data, sorry, in these two languages, it was still not too bad. But then we realized that since we started seeing these negative numbers, the decoder, the fact that the decoder has to decode multiple languages is much more of a constraint than the fact that the encoder had to encode multiple languages. So the bottleneck seemed to be in the decoder side when you're trying to predict sequences in different languages.
I'm confused. On the English to French,
Right.
why does it do better with no oversampling than with oversampling?
Because with no oversampling, the English to French is about 7 times more data than English to German. So it kind of hijacks the multilingual model. And
I see.
yeah,
Of course.
yeah. So now we did, okay, what if we did both directions? We do many to many. There's a lot of numbers on these slides, but it's still interesting that a single model, a multilingual model that can model these 4 language pairs is almost comparable in quality to what single different models could do. But it's not that you get better performance, it's just you get comparable performance with losses everywhere, right? And we wanted to push this thing to the limits. We said, okay, what if we take our 6 largest languages, so that would mean 12 pairs in every direction, and we put it into a single model the same size as that of a single model, right? So this multilingual model, you can see this blue column, there's like minus 3.5, minus 2.5. It's significantly worse than the single system. But it's an unfair comparison when you think about it. So the 12 single models combined have a total of 3 billion parameters. But this one multilingual model just has 300 million parameters, right? So we wrote in our initial paper that if you build bigger models, this difference is going to go down. That's what we had written. We believe that if the model was bigger, it would do better. And then we sent it out for review, And the reviewer said, oh, you keep saying it's an unfair comparison. Why don't you increase the model size and show us that it improves? But then once you increase the model size, it's going to take even more months to train, right? Well, we did know that this question was coming, so we started training these models before we sent them out for review. By the time it came back, the models were converged, right? So here you see that the multi-model, which is the standard size, the single model, it has about 3.3 billion parameters because it's modeling 12 different languages. There are 12 different models. And then a single multilingual model has 255. You see that the average loss in blue score is about minus 1.7. And as you keep increasing the size of the multilingual model, the loss keeps going down. And now you could ask, oh, why didn't you keep going further till it became greater than, oh, again, it takes months to train. Maybe the next time I give you the talk, the model would have converged and we'll have better numbers. But the fact is that if you throw more parameters at the model, it'll be able to model all of the languages. That was an interesting, expected observation. So here's how it looks. So when we train these models, you would have a lot of English to Korean data. You would add the token, and then you'd have Korean to English data. You'd add the token to indicate that it's going to English. You add English to Japanese data. You'd add the to Japanese token, and then you have Japanese to English data, to English token. So we started merging these languages together. We started adding the token and building these multilingual models. This is during training. So when we were training, we just did this, and we asked the question: can this model do more at test time? So this model that was trained on these 4 language pairs can now learn to translate between Japanese to Korean and Korean to Japanese without ever seeing any examples between these 2 languages. So essentially, we took a Japanese sentence, and usually what the model saw was the to English token. We would ask it to translate to English, and we said, hey, we're going to cheat you. We're going to say to Korean now. Can you translate to Korean? And it actually did it with pretty good accuracy. And we call this zero-shot translation because in machine learning, when you use a lot of data, it can do something. When you just use one example and the model learns that example, you call it one-shot learning. But when you don't have any examples, it's zero-shot learning. You had a question? Okay. So we were experimenting with the quality of this zero-shot translation. So it's not all rosy. It's not like you get the best translation, right? So say you had a multilingual system that's trying to model 2 language pairs. In this case, the language codes are English to Spanish, Portuguese to English. I'm sorry about the language codes everywhere. And then we said, can this model actually translate from Portuguese to Spanish? It did not see any Portuguese to Spanish data when it was trained, but during test time, can it translate? And we get a blue score of 21.6. It seems pretty high, right? Yeah, 21. We said, oh, wow, this is awesome. So now what we do is we have another model where we added the other 2 language directions. So when you think about it, this model, the first model, is learning to encode Portuguese, and it's learning to decode Spanish. So you can say, hey, wait a minute, it learned to encode Portuguese, and then it learned to decode Spanish. It's obvious that it can translate between the 2. It's just that it did not see any examples. And now we said, what if we taught it to decode Portuguese and encode Spanish? So in the bottom model, you're actually adding the reverse. You're not adding encoding of Portuguese and decoding of Spanish, but you're adding encoding of Spanish and decoding of Portuguese. So if the model was just trying to memorize these sentences, Portuguese to Spanish on this side to this side, this shouldn't help, right? But then it actually got better quality. So this means that the model actually has some sort of representation that is beyond just these Portuguese, Spanish languages. So any data that's added to the model is helping the model generalize in the zero-shot direction. Just for comparison, right? Previously, Google Translate, when it builds these models, we only have data from English to a language and a language to English because it's hard to get data. Well, Portuguese to Spanish may be easy, but it's hard to get data for Portuguese to Vietnamese, for example, on the web. You cannot go onto the web and try to find parallel documents in Portuguese and Vietnamese. So if you wanted to serve something like Portuguese to Vietnamese, what we would do is we would take a Portuguese sentence, translate it into English, and then we'd take the English sentence and translate it into Portuguese. We call this bridging. So we always bridge to English. So the phrase-based system, if it did bridging for Portuguese to Spanish, it would get about 28.9. So doing bridging is much better than the zero-shot translation, right? So the zero-shot translation is not the best quality. And if you had two neural systems and you bridged through English, you would get even better translation quality. And if you took all the Portuguese to Spanish data at your disposal and you built a separate system for that language instead of bridging, you would get even better quality, right? So why do you get better quality when you build a separate system? Because there's loss of information when you go through English. For example, if you go from Japanese to Korean, if you translate the Japanese sentence to English, you lose all formality information because Japanese has formality, but English does not have formality. And so it's a lossy process. So what we did was, hey, we have this zero-shot model on the left at the bottom. What if we gave it a few examples of Portuguese to Spanish just to fine-tune the model? Can it do better translation of Portuguese to Spanish? And with just a few examples, 5% more examples, and if you train it for about 1% of the time that the original model takes, you get better performance than all of the previous approaches that you had at your disposal.
But no blue scores to show us that?
So 31.77 is the model plus inc. Inc is incremental training. We incrementally train on a little bit. Yeah. So then we said, okay, this zero-shot translation is interesting. Can we actually look into the internal representation of the model and try to figure out if it's actually doing this language agnostic thing? So this is a hard diagram to explain. I've tried a bunch of times. I'll do my best. So what we did was we took a bunch of sentences, say 1,000 sentences, and we had translations for them in 3 languages. We had the same sentence in English, the same sentence in Japanese, and the same sentence in Korean. And we would pass 3 sentences through the model and get the internal state of the model, and we would plot it into a high-dimensional space. So in this diagram on the left, figure A, every sentence, every group of sentences, every group of 3 sentences in 3 languages is one color. So you can see that there are some clusters, like there's this cluster on the left, that's one color, there's the green cluster, there's a yellow cluster at the bottom, and then there's this red cluster. So each cluster is 3 sentences that based on the internal representation of the model, right? And then so let's zoom into one of these clusters in figure B, right? And then in figure C, to make it easier, we color code these sentences based on the language. So here you can see that the orange is the English, and then the blue is the Korean, and the red is the Japanese sentence. So it's the same sentence in all of these languages. But despite the fact that these languages have different scripts and different grammars, the model sees them the same because it's clustering them into the same space. So this sort of gave us proof that, oh, even though these sentences are in different languages, if they mean the same thing, it looks the same to the model.
When you're mapping to like multi-dimensional, higher dimension space, what are the dimensions in the case? I mean, I get the clusters, the colors, and everything like that.
Right.
But essentially, how is it being mapped?
So it's a 1,000-dimensional vector that we take, and
Which 2 are these?
no, I mean it's a 1,000-dimensional vector, and we t-SNE it down to 3D. We use t-SNE to compress it to a 3D plot. Yeah, and essentially the vector that we take is actually is based on the attention. So every time the model is trying to translate, we take the representation of the model that's attending to in the source side. Yeah. So there's more analysis, more dots, right? So I'll try to explain it well this time. So on the left, you have this diagram. It's the same, where you have these blue dots are translations from Portuguese to English. And the yellow dots are translations from English to Spanish. And now the red dot is what we call the zero-shot translation, right? It learns to translate from Portuguese to Spanish. So we took these translations and we mapped them into this space. And you would expect that since all these sentences are the same, it's the same Portuguese being translated to English, it's the same English being translated to Spanish, and since they're all the same, you'd expect them to be on top of each other, right? But then this is actually, it's a 3D plot. We zoomed into the worst part. It's not like all of it is on the right. But we noticed the huge cluster on the left, which is far away from the blue and the yellow dots, right? So there's a huge cluster of red, which is the zero-shot translation that's far away from the original translations. And we looked into it and we saw, hey, can we measure the distance between this red dot and the blue and the yellow dot that it corresponds to? So if you had a Portuguese to Spanish translation, how far is it from the Portuguese to English translation and the English to Spanish translation? And we noticed that the farther away in the space that the red dot was, the lower the quality of that translation was. And the closer it was to these Portuguese to English and English to Spanish translation, the higher the quality, which is what you would expect. So if the model is learning some sort of representation, you would expect these zero-shot translations to be close to the parent, but not far away. So there was a correlation between blue score and the distance from these things. Interesting thing is why don't we add the source token, which was the question asked before. So now the model is source agnostic. So if you had a Japanese sentence that translates to I'm a student at Tokyo University, you had a Korean sentence that translates to the same thing, you can do this kind of mixing or code switching between Japanese and Korean. Uh-huh.
The embedding like the final output of the encoding phase?
It's actually the attention embedding. So when you're trying to decode, you attend to all of the source tokens and you compute a weighted average across all the source. That's what we map.
So those are the activations of the nodes that translate between the first part of the translation process and the second part of the translation.
Yeah, that's right.
So each dot is like the attention
at one time step.
One word.
Yeah.
And you can encode that in just 1024.
Yeah.
It's amazing.
What if the source, like Hindi, is in English font?
Yeah, that's a good question. It actually depends on the data, right? So if in your data you see a lot of examples with Hindi in English font, you learn to translate Hindi in English font. But if there's not enough data of that representation, you learn to not translate. So in this case, you have a Japanese to Korean multilingual model, and now you can handle this kind of code switching. So if you had a Japanese sentence and you'd switch to Korean, I don't think anyone would do that. This is just for an example, but the model can still process this sentence because it does not care. As long as you say, translate this segment to English, it can do it perfectly. Then we said, okay, we're mixing languages on the source side. Can we mix languages on the target side, right? And this was mostly work done by Maxime, who's sitting here. And the interesting question there is the token that represents what the target language is going to be is just this one token that's saying, hey, this is going to Japanese. And then there's another token saying, hey, this is going to Russian, right? So we started experimenting with this linear combination of these tokens. So if you had an English to Russian and Belarusian model, or if you had a multilingual model with all the Russian-related languages, you would take the Russian token, you would add a weight to it, and then you would take the Belarusian token, you would add a weight to it, and we would sum it up. So we'd go from, in the table, you see going from 0, so that means it's completely Russian, and then if you go to 1, that's completely Belarusian, right? And in the middle, the model actually switches to Ukrainian, because when it's trying to translate from Russian to Belarusian, it goes through Ukrainian. It's like, okay, I'll go to Ukrainian, and then I'll give you your Belarusian at the end, which is very interesting. So more examples. So here we go from Japanese in W equals 0 and Korean at the bottom, W equals 1. And you can see that gradually the grammar changes from Japanese to Korean. And we asked about this to a Korean speaker, and he said at W equals 0.58, the model actually translates like a mix of Japanese and Korean. And at W equals 6, it translates it into Korean, but the ordering is similar to Japanese. So, so finally, it gives you the right Korean. Here's an example with Spanish and Portuguese. It's going from 0 equals Spanish, and then when you go to 1, it's completely Portuguese. You can see that some words change one at a time. So it's a gradual scale most of the time.
How do you encode that weight in the input?
So we take the embedding for this token, and we multiply it by 0.5. And we take the embedding for the other. It's all a vector, right? So we take the two vectors. Yeah, that's all the examples I had. So I have Some questions? Yes?
Yeah, so you talked about training,
Mm-hmm.
but I didn't hear you mention maintenance.
Maintenance?
Yeah.
Well, what do you mean by maintenance? Do you
Well, so, I mean, let's leave the influence of the Google Translate out of the equation. But languages change.
Right. So,
if you train a language at time A, it wouldn't necessarily be the same at time B.
Yeah. That's a good point. So, an interesting joke inside the Translate team is, for our team, the president is still George W. Bush, because that's what the data on the internet says. So when we mine these examples, when someone says President of the United States, it's George W. Bush. That's what we spit out. So it depends. You should get the right data. So we have to keep mining new data, and we have to retrain these models with the new data.
So that's what I mean by maintenance.
Yeah, so you'd have to retrain it.
So how often do you do that?
Because we just switched to these neural models, we haven't maintained them or swapped them yet, but we would do it every few months, I believe.
Okay, and then the next problem is if we bring Google Translate back into the equation, how do you make sure that you're not training the world rather than the world training you?
What do you mean by that? As in producing the wrong text for other people to learn?
So you go to the world, you develop a probability map, and then your probability map is not an exact representation of the probability map in the world. It's off by some degree. You use it over and over and over again.
Right.
And just by constant use, it's like the big lie. You say it over and over and over again, and it becomes true.
Yeah, that's a problem, I guess. But
why is it a problem?
I don't know. Like language keeps changing, and we can change our data to update the model.
It's a problem for maintenance to know whether you're looking at yourself or looking at the world.
But the practical manifestation of this problem, the practical manifestation of this problem would be that Google Translate trains on its own translations, which already happens. And as Melvin said, we know already that this is a problem. And the fundamental question is, can you distinguish human translation from machine translation?
I don't think that's the only issue, right? So if Google Translate were to be over-indexing on the outputs, certain words, right? And then people grew up learning through Google Translate.
Right.
Wouldn't they start to use those words more?
Yeah, that's true. I mean, one way to solve this is we have this community thing where people can actually go and edit the translations, and we learn from those much more than our actual data. So if we had 100 examples of something, but if one human went ahead and said, hey, this example is wrong, this is the right one, we learn much more from that example.
Going back to my earlier question about tone, where age and masculinity and femininity.
Yeah,
if your system go on like that, you're going to wipe out the language because you have basically neutralized the voice.
No. So one of the things that we're actually doing is when you have this multilingual system, we just add this token that says, oh, hey, go to this language, right? One of the other things that we experimented with is you can add a token that says, hey, translate it formally, and it works. So it learns from examples that this sentence has to be, if you put the token that says formal, it has to be translated formally. And we put another token that says, hey, this is a male person. You put a token for male, it translates it into a male.
How do you know that in the first place?
We would get it from the data. So, for example, formality, you know that some pronouns are used in the formal sense, some are in the informal sense. So you'd have to get it from the data. You'd have to have a mechanism for detecting these things.
So coming back to your token, it seems like a lot of the power you derive is just from that simple token you add at the beginning. So how do you train that token?
It's just trained it's not trained in any special way. It's just one of the characters in the sequence, one of the words in the sequence. So there's no special handling.
So what kind of a cost function do you use to guide decoding during beam search? And if you've done ablation studies, like you penalize longer sentences, etc.
We do some sort of length normalization to handle the different lengths. Is that what you were asking?
Or in general, like do you have different cost functions you use during beam?
No, it's just one.
most singular English nouns are preceded with an article.
Uh-huh.
Why is it that your Hemingway example in the very beginning had trouble?
Yeah, that's a good question. So one of the things could be that the data is just like that. So most of these things you just point to the data, right? So it could be the case that the translations of Japanese to English on the web, people omit articles or things like that. Well, there are many other data problems. Like, for example, if you looked at examples from English to Hindi, then you'd see this weird odd case where people who are translating this Hindi word would, instead of translating, they would try to transliterate it into Hindi. And now you feed this data into the model, it learns to do it the same way as it was in the data. So.
Have you looked at domains at all?
Yeah.
So, I mean, I would think that technical material would be a different domain and have a different property than poetry, for example.
Yes. We train on all the data we have. We train on all of the data that we have, but we are starting to look at training on different domains and specializing models for different domains. You had a question?
There was a question earlier about stability. If you translate from X to Y and then translate back.
Mm-hmm.
I would think that there must be a fuzzy gray interpretation of what a translation is.
Right.
And I would think that maybe one way you could automatically hone that down
Mm-hmm.
is not by taking just the single quote best translation,
Mm-hmm.
but take the top 2 or 3 or 10.
Mm-hmm.
Take each of those, translate back to the source language, and take the top 2 or 3 or 10. So you have 9 or 100 possible circuits.
Yeah.
Compare those with what you started with,
Mhm.
and see to what extent, try to match them up and see which ones are bizarre versus
Right.
which ones seem to, for an adjective or something,
Yeah.
it might come back as
Right.
the same or a different, and
Yeah.
that would tell you
Yeah.
which route perhaps to weight more heavily.
That's a good question. We do use beam search when we decode. So when we decode these neural sequences, it's not like you're picking the top one. You always pick 1 out of 8 or 1 out of 4. And there are a lot of gains from doing the beam search that just pick the top ones.
Can the source be audio?
No, not in this model. Not yet.
Otherwise, you could solve the previous question, English font,
Mhm.
Hindi, audio coupling it to audio, and then.
Right. Yeah, that would be awesome if you do speech to speech. Right.
It's a dumb question.
Mhm.
What happens if you translate English to English?
It kind of learns to paraphrase a little bit.
Just zero change? Or?
No, it paraphrases a little bit. So we did look at it. It learns to paraphrase. So something, I had some examples that I didn't put in the slides, but something like takes a long time, gets paraphrased to too late or something like that. It does the small things, but most of the time it copies the words. But in some cases it paraphrases.
I was never much good at foreign languages, but as an engineer, when I learned the very basics of some other languages, I kept wondering if there was a way to evaluate what language is best in some weird aesthetic sense. The most explicit, the most alternatives, the clearest vocabulary, the least ambiguity.
Right.
I'm wondering if this system gives you some way of trying to answer a question like that. If you said you use English as an intermediate language, you might try using several other languages as the intermediate and evaluate to what extent the results are more reliable if you go through Russian, for instance,
Right.
because of the.
But that's the question, that in this model it's not going through English. It's going through this interlingua that it learns on its own.
Okay.
So instead of forcing the model to go through English, you're saying, hey, go through whatever you think is best.
I didn't mean for the sake of making your product work better. I
Mhm.
meant for just aesthetically answering the philosophical question about what language
Yeah,
is the most.
it could be interesting. Like one of the things someone was telling me was there was this paper that said all languages have the same, they try to reduce the dependency length. So people, when they speak the language, they try to make the sentence as short as possible. So they were saying that, can you use this model to prove it, that all languages have this kind of thing? So we could use it to do those kinds of experiments, but we haven't yet.
What do you do without a vocabulary words?
Say that again.
Out of vocabulary words,
So-
words you've never seen.
Yeah, so what happens with these word pieces is as you're at the top, they're mostly words. As you go down the frequency list, they get split up. But as you go below, there are characters. So when you have out of vocabulary words, the model tries to make up these characters. So that's kind of neat in that when you had a proper name, it would transliterate it into the target language. Instead of trying to learn that name, it would just copy the characters.
Just curious. So you have these various languages, and say you're expressing the same idea in all these languages. So a language is like a camera, and the sentence in that particular language is like a picture of the actual object, which is the idea.
Okay.
Right. So is there something? So have you like tried to figure out how the idea and the language can be decoupled in a certain sense?
That's a good question. Well, we're doing some of it in that this representation is kind of language independent. It doesn't depend on the script, it does not depend on the sequence of characters, but it depends on this 1000 dimensional vector of numbers, of floating point numbers.
So, you said that you get your material for training from the web.
Yeah.
And then you used an example of BBC having the same material in different languages. So that's all very current. Now Google's also got this project taking the written library and converting it. Are you using any of that material?
So because of legal reasons, we're not supposed to use Google Books.
Even if they're 100 years old?
No, for some sort of legal reason. We've been trying to use it for a long time, but we cannot use it. I guess we'll figure it out. But I think we cannot use it for legal reasons.
Your feedback mechanism, is that automatic or they just call you and tell you the translation was wrong?
No, if you use the app or you use it on the browser, you can just press it and type the correct translation.
No, I mean, it goes to the system or you just look at it later?
No, we collect all the examples and it goes into the system again the next time we train.
You control the flow?
Yeah, we control the flow. We have, so when someone gives a correction, what we do is we have this thing called community, where people who love their language, say I love Hindi, I go to translate community and I can, when I'm free, I can give translations of sentences. So we show them these corrections that other people did. We say, hey, this person said this is the translation of this, what do you think? And if multiple people say yes, this is the right translation, we accept it.
So you're not using all like 103 versus 103.
No,
you have
no.
smaller groups, and I imagine those break down to like Romance languages versus not.
That's a good question. So right now we are grouping according to language family. Well, we did experiments. Like I did a lot of experiments that tried to put Korean and Portuguese together,
right?
And it was still the same quality. So it does not care about the language.
And if you
family.
throw in like Basque or one of the sort of the strange.
I didn't do any extreme ones, but you know, but it doesn't seem to care that much.
How about Fortran?
No.
COBOL and APL.
We'll try it.
Did you try any, I don't know, humor puns?
No. It's pretty bad at it, I think.
So, is there a reason why you use a one-hot encoding for the result instead of something like word-to-vec?
No, all of these are vector representations. They're not one hot.
No, at the end. So you pick a single one from the list, right?
Right.
So is it? I mean, there are already embeddings of words in semantic space that will presumably have like a smaller amount of output parameters, right?
Well, when you pick from these different vocabulary elements, like 32,000 of them, right? You pick one of them.
Yeah.
But these 32,000 word pieces are represented as an embedding.
Oh, okay. So it's not.
So you pick.
It's not a one hot.
No, it's not a one hot. It's an embedding. Yeah.
So, I mean, this is a very simple question in terms of machine learning thing, but it's like how much weight do you give to like words which are pretty rare? So, if you've seen only like a couple of examples, do you think that can get suppressed?
It does tend to get suppressed, and that's a problem. And one of the things, one of the ways you can solve it is you can weight your examples based on how important they are, but we don't do that right now.
Well, there's also one factor that because we use this statistical subword segmentation, the distribution of frequencies of these 30,000 species is much more uniform than the zip distribution you will see if you looked at the language itself. So we hope that it can learn something meaningful about each of these species, and when the infrequent word consists of many of these species, we hope that some of them have shared meaning with other words. Like the stem in the word will occur many more times than this particular complex form which is using that stem. But mostly just hope that it works.
Yeah.
How about words exploding into phrases? For example, in Intuit, I think there's 37 words for sound. And if we try to translate them into English, some of those words turn into phrases and some turn into sentences.
Right. Again, because we use these subwords, we would handle them.
So would you get?
Well, you would get whatever is based on the context. So if the training data is saying in this context always translate it into the phrase, then we would throw out the phrase. If the training data says in this context give a word out, we would give a word out. So let me conclude because I'm running low on time and then questions. So we show that GNMT, which is Google's NMT system, leads to a huge leap in translation quality. Multilingual NMT allows us to do zero-shot translation. So visualizations that we did, they're hinting at the presence of an interlingua between these languages. And we've just scratched the surface of the interlingua. There's a lot to do. We need to explore more. And there's a lot of interesting problems to solve in the coming years. Well, this could be what the future looks like. Instead of having a machine translation system, you could have a single system that does multiple tasks and in multiple languages. So you can have a system that can translate from English to Spanish. It can also do English sentiment. It can do English parsing. It can also do German parsing, things like that. This could be a reality, right? There are some resources here, some links to articles, some blog posts, and thank you very much for your invitation. Invitation gets lit up here.
The papers mentioned they're out already, correct?
Yeah, for 16 languages. And yesterday we launched 3 more languages, Hindi, Vietnamese. Yeah, we're launching more and more languages.
How does the numbers compare versus like Skype translator?
Yeah, I mean, I don't think I can comment on it. I don't know, like how. No, we only know their quality if they do it on a public data set that we also have access to, right? Yeah. Well, we believe we're better, but. Yeah.
So what about local dialect? I mean, like in Hindu and Chinese, there's tremendous amount of local dialect.
Right. Yeah, we don't handle it right now, but one of the sad things is language is kind of weaning out, right? These dialects are not, most of the time they're spoken, they're not written, and there's not a lot of data on the web. So the only way we could pick up this dialect is if there was data on the web and we see it. You have a question?
Yes. Have you tried running using emoji, which is sort of another kind of like there's some debate whether or not.
Oh, it does learn to translate the emoji. So it splits up the emoji and then copies it. It learns to copy the emoji most of the time.
So you have seen it going. So English into emoji or
Oh, no. We haven't translated emoji across language, no. No.
Emotion detector we're having.
Yeah.
It's difficult to find parallel data for emoji. That's the main problem, and it's also difficult to classify data into dialects.
So wait, is the difficulty finding things that are in English translated into emoji?
Yeah.
Oh.
Yeah.
I mean that I can help with.
Question, you had a question for Melvin.
I'm not sure this has practical value, but it might be intriguing and for historical values to introduce Esperanto into the mix. And have you done that?
No, that's a good question. I'm working on a side personal project where I'm trying to do this, but no, we haven't done it.
12 people in the world.
The
World's least popular
The Colloquium isn't very much Esperanto data examples, are there?
Yeah. No, there are not many, yeah.
Don't we speak Esperanto?
Have you tried translating poetry? Like, does it preserve the aesthetics, maybe?
Not so well, but most of the time, yeah. You get the idea of what the poet is trying to say.
Wouldn't work on haiku.
I don't want to keep hogging.
Oh, no.
Okay. Towards the beginning of your presentation, one of the things I was wondering was the extent to which the engineers and architects were themselves multilingual in a broad range, bilingual or multi, thinking that that would help them understand the problems.
Right.
But as you got into it, I'm thinking that one doesn't need to understand the problems if one is designing the network and then turning the crank until it comes out. So
that's a fair point. We don't have to know the language to do this.
Is there value, or do you have multilingual polyglots or whatever working on the team, and do they have any insight into what the issues might be?
I can speak a few languages. Maxime, I guess, can speak a few languages. But there is value in that. If you see something wrong, you can immediately spot it instead of trying to send it out to do these evaluations and get it back.
What languages, for instance, do you consider yourself?
Me? I can speak English, Hindi, Tamil, and a little bit of German. I think Maxime can speak French, Russian, and English. Russian and French and English.
That's pretty good.
You guys are doing far better than the founders of AI. McCarthy knew Russian.
Okay.
Minsky basically only spoke English.
Right.
Well, then my follow-up to that, with your questions, is that this really does go back to some early AI thought experiments. I don't know if this was Turing or someone else, the idea that a man in a box that was seeing slips and looking at answers and finding out how to match the patterns.
Chinese room, this was John Searle. John Searle.
In a sense, that's what you're doing here. If the coders don't understand this, they're just finding something else to match one thing against something else.
Right.
So maybe this is a dumb question, but isn't this a fairly sophisticated AI system that would pass the AI test?
I don't know. We should test it. But that's the point. That's a good point. It's that the model does not know what language it's seeing, but it can do what it's asked to do.
Can we ask it from same language back to the same language? That this person really means to say this.
If you train it enough, yes.
Trump is input and...
no comments.
Would it be possible to add a structure to some of your data, I suppose, that this piece is a poem, this piece is a technical article?
Yeah, I mean,
would that make
it would definitely help. And one of the things you can do is if you tag these examples based on some domains, and when someone is trying to translate, you can give them the option to say, hey, this is the tech domain, give me the best translation. So then we can do the best translation.
Can you speculate on applications to other domains? And what I'm thinking is genetics, where you can learn to translate a sequence of protein 1 in humans and macaques, for example. But is there anything else that you're excited about?
Yeah, I mean, one thing that's interesting is as long as you have enough examples, I think the system can learn by itself. So if you had enough examples of human to animal genes, it can do a pretty good job at it. All right, I think people are tired of questions. T16, by that point, the 90% of the winners were neural machine translation systems. So it had already started to change. And people were trying to do zero resource neural machine translation. Then we had Google's paper and the papers on fully character neural machine translation. And finally, the zero shot translation. But you can see that there's a lot happening. A lot of people are looking into it. And it's an interesting research topic. So just a step back, what is sequence modeling? So you want to predict the likelihood of a sequence. So what is the probability of this sequence, right? And a sequence can be a picture, a video, some speech, or it can also be a piece of text. The typical example is a language model. So in a language model, you want to say how likely is a given sentence. So you will model this as a product of these conditional probabilities. And in an n-gram language model, you would have the nth order Markov assumption, which is that you only depend on the previous n minus 1 words, and you don't depend on anything else. But we want non-Markovian sequence modeling, which is, in Markovian modeling, we ignore anything that's beyond the context. But in non-Markovian, we want to support multiple variable length sequences. So you would end up having to model the entire sequence, right? And they have to be variable length. So what's one way to handle variable length sequences? You use recurrence. And that's where these recurrent neural networks come into play, called RNNs. So here's a small example. If you wanted to model this sentence, the cat sat on with an RNN, you'd have the input sequence, and then you have an internal memory state, which is the one in purple, that keeps track of the state at each time step. And then you need a function that takes at each time step the input and the memory state, and it can recurse at each time step. So you'd have probability of the, and then you'd have probability of cat, given everything else, probability of sat, given everything else, and so on. Some more information about RNNs. They technically have unlimited depth because you can unroll the RNN.
Can you go back one slide?
Yeah.
So in order to do that, you have to have a vocabulary.
Yeah.
And you have to have a complete representation of the vocabulary.
Yes, we do. So this talk is based on our paper, which is titled Google's Multilingual Neural Machine Translation System. And then we have a colon, and we say, enabling zero-shot translation. So my name is Melvin. I'm from the Google Translate team. But this is joint work done with many people from the Google Brain team and the Google Translate team. First of all, happy International Women's Day to everyone. So why do we care about translations? So about 50% of the internet is in English, and only 20% of the world's population speak English. And on the right, you see this graph. These are the top 10 languages on the web. English, Chinese, Russian, German, Spanish, Japanese, French, Polish, Korean, and Portuguese. And they make up about 80% of the web. And you notice that languages like Arabic or Hindi, which makes up about 300 million speakers each, they're not even in the top 10. So Google's mission is to make this information accessible to everyone. So we definitely need translations. About Google Translate is we have about 1 billion translations every day. And we have about 500 million monthly active users. And we support about 103 different languages.
Question on your last.
Yeah.
So I've actually spoken with Portuguese, and the thing they point out to me is the vast majority of Portuguese are in the Brazilian domain, like
Right.
5 times as many.
Yeah.
So you're saying that, are you using the PT there or any of the others?
No, we club both of them.
Okay.
It's not, we don't distinguish.
That's fine.
Yeah.
That was not clear.
Yeah, and please ask questions. I have a lot of time. Yeah. I have a lot of time, yeah.
Country code, language codes, not country codes.
So about this slide, one interesting thing about Google Translate is one of those products where 95% of usage is outside of the US. So our top countries are like Brazil, India, Mexico, Germany, Italy. But you'd expect every other Google product has 90% usage in the US and 10% elsewhere. How do I know it's you? Well, machine translation, you're going to say D, and then again, you predict what's the second, given that I predicted D, Katsa, and then the next word. And you keep doing this until you encounter an end of sequence token. So when the model produces an end of sequence token, we say, oh, okay, we're done decoding. Here is the output of the model. So you can stack these sequence to sequence models. So you can have, instead of having just one of these layers, you can have multiple layers stacked on top of each other. And yeah. And then there was a bottleneck that I talked about because here you see the encoder is trying to encode the entire sequence. And then when you want to decode, we use this mechanism called the attention that is trying to pay attention to every input in the encoder. So when I'm trying to predict the first token, I can cheat and I can look up every one of the encodings that I want to look at. And the darker the line, the more the attention it's giving to that sequence. So when you're trying to predict the first word, say knowledge, you would want to pay attention to the Chinese word that means knowledge much more than the other words. So you can see that there's a dark line and then.
Question?
Yeah.
But you don't look backwards?
You don't look backwards?
When you're in the second one, you don't look at you don't look back one in the sequence.
You do look back at the last token you predicted.
Okay.
Yeah. Yeah, you do. Like you know what you predicted previously. So when your decoding is, you know what.
In the last one, you don't look all the way back.
You don't look all the way back. You just look one back.
Actually, if you look at the pictures, there are lines which go to each source word, but some of them are almost transparent because the weight of this is 0. The way it is implemented, it computes a weighted sum over the source sentence.
The grade to the point of flight.
Yeah.
Well, I see. So the words that are closer to it probably influence that word, so they have a higher weight.
Yes.
And the ones that are further away have less influence
No,
on
it
the current
depends
context.
on the ordering. So
Right.
It's similar to how a human would do it. So when you have a long sentence, you read the entire sentence, and then you start translating, and then like, oh, I forgot what I had to translate. I go and I look back. It's like, okay, I have to translate this segment. I translate it, and then you say, oh, I have to translate this segment. I go, I look back. You kind of give a mechanism for the model to attend to different things.
This is a mechanism that's called soft attention because it computes probabilities.
But that may work for French because of the Académie Française, but it doesn't really work for English because English is constantly creating new words.
That's a good point. So I actually get to that in a bit. But that's an interesting question, right? If you have a machine translation system or you want to model a sequence, you need to have an open vocabulary. So you need to support everything, right? And I get to that in a little bit. More information is they have unlimited depth. They're general computers. So they're also universal function approximators. So they can learn any program. So you can think of it like this. There's an input at every time step, and then there's a recurrence, and it outputs a memory state that you can use. How do you train this RNN? Is you unroll the loop, and you apply back propagation as you do to every other neural network. So you would back propagate through time. And these RNNs have problems in that they have this problem of vanishing or exploding gradients. Since the sequence is too long, as you go further down the sequence, your gradients can explode or vanish. And as the name suggests, you need a long-term memory, which is why we use long short-term memories. They were founded back in 1995, but they're very popular now. So this is what we use. So this is a vanilla RNN, and then there is an LSTM RNN. But for most practical purposes, you can think of an LSTM as a black box, which is just a better RNN that you can use. And from sequence modeling, now you want to get to sequence modeling. So you have an input sequence, and then you want to map it to an output sequence. And here we call the left side what is called an encoder. The encoder is trying to encode the input sequence. And then on the right side, you have the decoder, which looks at the encoding of the input sentence and tries to predict the output sequence. And since we already said, because we're using an RNN, we can support any sequence lengths in both the input and the output. So here's the encoder, which is in pink. So the cat sat, and you can see that at each time step, you're trying to model the sequence. And at this point, this representation you're actually modeling the entire sequence in that representation, in that one vector. It's a vector of about 1,000 numbers, and you're modeling the entire input sequence in that one vector. And now you want to decode. So based on this, you want to predict, oh, what is my first target token? So it started with Warren Weaver in 1949. He used this tall towers analogy. So you're in a tower on the left and you want to communicate with someone on the right. He says, do not shout from tower to tower, but go down to the common basement and try to talk to each other. And he was hinting at some kind of an interlingua which exists in the basement. And let's look at a brief history of machine translation. So it started with in the 1950s, and then 1960s, Systran, which is the first machine translation company, was founded. In the 1990s, people were doing IBM models, word-based models, and then people started doing statistical MT. And in the 2000s, there's this thing called phrase-based machine translation that became very popular, and that started being the state of the art for over a decade, actually. And then you started seeing applications that started to use deep learning, which is using these neural networks. And the first success was in speech recognition, but slowly it caught up to machine translation. So about 2014 was the first neural machine translation paper. And then 2016, there was our paper from Google. But a lot has happened between 2014 and now. So here is, well, before that, here is a quick intro about what phrase-based machine translation did. It split the sentence into a bunch of pieces, and it translated phrase by phrase. And at the end, it tried to put it together like a puzzle piece. So it translated one puzzle piece, the next one, and then it tried to stitch it together. But when you have a neural machine translation, this is an exaggeration, but you can think of it as a painter trying to paint it from scratch. So it's trying to make continuous and a global decision instead of making these local decisions. Here's what's happened in neural MT from 2014 to 17. So you initially had the first paper come out, then there was a paper on large vocabulary, NMT. Then we saw the same architecture being used for image captioning. OpenMT in 2015 was the first public competition that had a neural system in it. WMT15, also the first WMT that had a neural system in it. A bunch of work on subword neural machine translation. People started doing multilingual neural machine translation, multi-source.